Welcome to Control Charts 101, your introduction to this essential continuous improvement tool brought to you by the Systems Thinking Academy. In this video, we're going to cover the what, the why and the how of control charts. So let's begin with the what. What exactly is a control chart? Well, put simply, a control chart is a time series chart, but with extra data series added to it. Now what does that actually mean? Let's use a simple example, a factory that manufactures widgets. Every day the factory manufactures a certain number of widgets, and every day a certain number of those widgets are detected as being defective. So like any factory concerned with improvement, it measures the number of defective widgets that it produces per day. So let's dive into a sample of defective widget data plotted over 20 days. Here you see the data in a table, and here you see the same data plotted in a time series chart. Let's take a moment to absorb what the data is telling us visually. We have a run of data representing 20 days worth of defects. Across those 20 days there is variation between the number of defects produced on any given day, with a spike on day 12 of 18 defects. To convert this analysis from a simple time series chart into a control chart, we need to add 3 additional data series. First we add the average, then the upper and the lower control limits. Let's talk about each of these elements in turn. First of all, the average. There's 3 types of average available to us: the mean, mode and median. In nearly all instances in control charts, we use the mean average. It's sometimes appropriate to use the median. For example, if we have a very small sample size combined with very high variation. But let's just treat the default as being the mean, not least because the mean is the most commonly used type of average in business intelligence reports. Now let's talk about the control limits, the upper control limit and the lower control limit. Notice they are both exactly the same distance either side of the average. Collectively, the data showing the defects, the average and the upper and lower control limits complete a control chart. So that's what a control chart is, but you may be forgiven for asking, well, so what? Why use a control chart? And that's what we're going to cover now. To begin with, let's take a look at the way that data like this is normally used in decision-making environments. There are 3 common usage patterns. Number 1, roll the data up into an average and then compare one of the values, normally the most recent, against that average. Number 2, compare one value against another equivalent value, commonly the 2 most recent values in a set of data. And number 3, compare a value against a target or a specification. Notice that each of these 3 patterns have something in common. All 3 are rolled up summaries of the data, with the detail having been removed. We turn to approaches, such as in these 3 examples, in the belief that it will facilitate decision making. But is that really true? Here's an example of pattern number 1 in action. In this pattern, we compare an individual data point against an average for the data series. And in the absence of the dimension of variation, this makes it impossible for us to determine the extent to which an individual data point falls between a predictable range, thus rendering any measure of deviation from the average as being arbitrary and meaningless. When we use averages in this way, we get ourselves into all sorts of trouble. Corporate folklore has it that a trade union body in the United Kingdom once made its stated policy that all workers should be paid above the average wage. And even in more modern times, organisational performance measures are often articulated as being a comparison between one value and an average over time. Usage pattern number 2, comparing one value against an equivalent value. Often it's one value versus its preceding value. This is otherwise known as the binary data comparison. Binary data in this context not meaning strings of 1s and 0s that you'd find in a computer, but simply meaning a comparison between 2 equivalent numbers. The logic of this method is that the value that you are comparing your number against is in some way a meaningful benchmark for comparison. However, seldom accompanied by any method that determines how meaningful the comparison actually is, this logic is thrown into question, and therefore the comparison becomes invalid at best and misleading at worst. Selecting a value for comparison just on the basis that it is equivalent to another makes that selection arbitrary. Yet this approach remains stubbornly commonplace in organisational decision-making environments. Pattern number 3. Comparing a value against a specification or target. Whilst the use of this method may highlight a deviation against a desired value, it provides no insight into the cause of that deviation and therefore any basis upon which to take corrective action, and often serves as a distraction for decision makers. So, there's our 3 common usage patterns and their associated downsides. And with those 3 patterns and downsides in mind, here's how a control chart helps. Now before we continue, let me just make the point that the use of control charts requires us to capture no data beyond that which we have already used in the 3 usage patterns we've just explored. It simply requires us to ask different questions of the same data. So that means all of the data that we need to create a control chart is already here for us. All we need to do is to use the data to calculate the mean and the upper and the lower control limits. Great. So what's it telling us? Well, quite a lot actually. But before we cover the specifics of what this chart is telling us, let's just talk about predictability. The essence of a control chart is its ability to provide us with an insight into the future performance of a process for as long as that process remains unchanged. In this instance, the upper control limit is 16.1 and the lower control limit is minus 0.7. Both the upper and the lower control limits are products of the underlying variation within the data and as such are able to give us an insight into the future performance of the process. Specifically, this control chart is telling us that on day 21, the number of defective widgets produced by this process will fall between the lower control limit of minus 0.7 and the upper control limit of 16.1, an insight that averages can never give us. But it's telling us more than that. What you can also see is that spike that we observed on day 12 is higher than the upper control limit. In other words, it is out with the predictable limits of the process. This is an example of a signal, and it's one of the key benefits of a control chart, namely that it enables us to differentiate between signals and noise, signals being the things that warrant investigation or corrective action, and noise just being the natural hum and variation of the process. Had we continued to use a binary data comparison, comparison against average, or comparison against specification, we would have interpreted variation within the normal predictable control limits of the process as being something warranting corrective action or investigation. It's for this reason that Walter Shewhart, creator of statistical process control, a method which includes amongst other things control charts, described control charts as being the voice of the process. Only the voice of the process is able to give us the insights that we need in order to improve the process. However, a control chart created and analysed in isolation is an example of taking data out of its context, and it cannot give us any answers. What a control chart can do is alert us to signals in the data and give us a robust method to differentiate between signals and noise. We want to act on the signals and disregard the noise. There are 4 types of signal that a control chart can alert us to, but this being control charts 1-on-1, we'll cover the other ones in a later session. So for the time being, just remember, control charts give us signals, they filter out noise. We want the signals, we don't want noise. So finally, how to create a control chart. Back to my previous point that a control chart needs no additional data other than that which we have already used to create a run chart. There are, however, a couple of intermediate steps that we need to take to calculate some values that will enable us to get to the control limits. So let's do that now. The mean is simple. We take the sum of the data points and then we divide that sum by the number of data points. In this instance, the sum of the data points is 154 and there's 20 data points, so 154 divided by 20 is 7.7, that's the mean. Next, the control limits. We can do these together because one is basically the inverse of the other, and that's why you'll always find the upper and the lower control limits are the same distance either side of the average, with one tiny exception which I'm going to share with you at the end. In order to calculate the control limits, we need to take an intermediate step. The first thing that we need to do is to quantify the variation, and we do this by creating a second run of data called the moving range. The moving range is simply a run of data that shows the difference between each data point and its subsequent data point. So, in our example, the value for the first data point here is 5, and the value for its subsequent data point is 7. The difference between those two numbers is 2, and so the first value in our moving range is 2. Now we just continue this calculation until we get to the end of the data, and what you'll notice is that by the time we get to the end of the moving range, we don't have 20 data points, but we have 19. And that's because there is no subsequent data point from which to compare the last value in the data set. Hence, you will always find that the size of the moving range is one value smaller than the size of the data set upon which it's based. Now that we have the moving range, our next step is to calculate the mean of the moving range. So just in the same way as we calculated the mean of the data, we take the sum of all the moving range and we divide it by the number of items in the moving range, which is 19. So that gives us a mean moving range of 3.2. Now before we go on to take the final step and calculate the upper and lower control limits, remember back to mathematics, a value called pi, 3.14159 and so on. It's one of those numbers that you just have to remember. And I'm going to share another one of these numbers with you now, which is necessary to create a control chart. The number is referred to as the scaling factor, and the number itself is 2.66. You don't need to understand why the number is 2.66, you just need to remember the number. To calculate the upper control limit, we simply take the average of the data, and then we add the mean moving range multiplied by the scaling factor to that number. So in other words, it's 7.7 plus 3.2 times 2.66. To calculate the lower control limit is exactly the same formula, but instead of adding the mean moving range times 2.66, we subtract the mean moving range times 2.66. And that gives us a value of minus 0.7. Now remember a moment ago when I referred to a tiny exception to the rule that the upper and lower control limits always fall exactly the same distance from the mean as each other? Well, that exception applies in this case. And what we've got here is a lower control limit that's lower than 0. Now mathematically that's perfectly valid, but thinking about the context of this data, we're talking about defective widgets. And of course it's not possible for a factory to produce a negative number of defective widgets. And this points to a really important principle about using data, which is always to consider the context of the data that you are analysing. In this context, it makes no sense for a factory to be able to produce minus 0.7 defective widgets on any given day. And so in this instance, the sensible thing to do would be to make the lower control limit 0. And effectively what we're then saying is that on day 21, we can expect this factory to produce between 0 and 16.1 defective widgets. And that's all the number crunching that's necessary to create a control chart. So there we have it, Control Charts 101. We've talked about what a control chart is, a line chart plus average and control limits. We've talked about why we need a control chart, and that's because it enables us to avoid the pitfalls associated with responding to noise in a process rather than signals in a process. And we've just covered the how. So this has been your bite-sized introduction to control charts. Watch out for future videos. I'm going to cover creating multi-stage control charts, how to spot those 4 signals I referred to in a control chart, how to create a control chart in Excel, and some more advanced topics around the statistical, mathematical aspects of control charts. So until then, thanks for watching. I hope you found it helpful. Any questions, comments or feedback, please pop them in the notes below, subscribe to my channel, and I'll see you on the next video.